Hello everyone, if you've tuned in for Woods Hole Oceanographic Institution's Ocean Encounters presentation on the Arctic, you're in the right place. Joining us from WHOI will be climate scientist Sarah Doss, oceanographer Isabella Labras, and marine biologist EVIE FACHON. Stay with us. Hi everybody, in just a few minutes we'll get started with Woods Hole Oceanographic Institution's Ocean Encounters presentation, The Arctic, Our Planet on Thin Ice. We've still got a lot of people joining us, so thank you for your patience. Hello, you've joined the Arctic, a Woods Hole Oceanographic Institution Ocean Encounters presentation. We have a lot of people joining us tonight, so please bear with us. We'll get started very shortly.
The ocean covers 70% of the globe. It gives us oxygen and food and millions of jobs. It brings joy and shapes our climate and weather. The ocean is life, and it belongs to everyone. Woods Hole Oceanographic Institution is the world's independent leader in ocean discovery, exploration, and education, working to understand and sustain one of humanity's most precious common resources. Join us today for our ocean, our planet, and our future.
Welcome to Ocean Encounters, an event series from Woods Hole Oceanographic Institution, or WHOI, as we like to call it for short. Tonight's event is the Arctic, our planet on thin ice. My name is VERONIQUE LACAPRA, and I'll be your host for tonight. WHOI's Ocean Encounters events are made possible in part by the Avatar Alliance Foundation and Dalio Philanthropies. Thank you. Our 5th season of Ocean Encounters has also been named an endorsed activity of the UN Decade of Ocean Science for Sustainable Development. I want to give special thanks to our WHOI members for joining us tonight. You are the heroes at the heart of our efforts. Before I introduce our panelists, I'd like to take just a minute to share some tips on how you can optimize your Zoom viewing experience tonight. Throughout the evening, our speakers will be taking questions from all of you. If you'd like to participate in this live Q&A, please use the Q&A button on your Zoom screen and type your question in the little window that will appear. You might be more familiar with the chat function in Zoom, but for tonight, please use the Q&A function instead. We often get hundreds of questions, so I apologize if we don't get to yours while we're live. You can ask questions at any time, starting now. I also want to let you know that we are recording this event. That recording will be made available on the whoi.edu website. We had more than 1,600 people pre-register to join us tonight, so you're in very good company. We also have viewers joining us right now on Facebook and on YouTube. Thank you, and welcome to everyone. Let's get started. The Arctic is feeling the heat from climate change more than anywhere else on Earth, with rising temperatures and melting ice putting increasing pressure on marine life, ocean currents, and human lives and livelihoods. Tonight, we're joined by 3 WHOI researchers who are studying the northernmost regions of our planet. They are Sarah Das, ISABELA Lebras, and EVIE FACHON. Sarah Das studies how climate change is impacting the polar ice sheets and what that means for the rest of the world. ISABELA Lebras is what's known as a physical oceanographer, which means that she studies ocean currents and the importance of moving water to the ocean and our planet. EVIE FACHON is getting her PhD from the MIT WHOI Joint Graduate Program. She's a marine biologist specializing in harmful algal blooms, also known as HABs. Sarah, ISABELA, and EVIE, welcome.
Thanks. Hi, thank you.
Sarah, I want to start with some geography just to get us situated a little bit. What do we mean when we say the Arctic? How big of a region is that, and what does it include?
Sure. The Arctic is a polar region. It's actually dominated by an ocean, by the Arctic Ocean, which is in fact where the North Pole is located. So if you imagine Santa Claus sitting on land, he's actually floating around at sea. This Arctic Ocean is surrounded by the northernmost continents, which includes 8 Arctic states and Greenland. The whole thing is about 6.4 million square miles in size. And as I said, most of that is taken up by the ocean. The Arctic is also sometimes defined as the area north of the Arctic Circle, which means the latitude above which the sun does not set on the summer solstice, so 24 hours of daylight in the summer, and does not rise on the winter solstice, so 24 hours of darkness.
All right, now I want to situate where each of you works, because you each work in a different part of the Arctic, and have you just briefly introduce what it is you study there. Sarah, let's stay with you for now.
Sure. So my work takes me frequently to Greenland, which is where I'm particularly interested in studying how changes in the atmosphere and the ocean due to climate change, both now and in the past, have affected the Greenland ice sheet. And in turn, how changes to the Greenland ice sheet due to global warming, which we're all experiencing, has increased melting and freshwater runoff from the ice into the ocean, and thereby affecting the rest of the world, because the ocean connects everywhere through its currents. The Greenland ice sheet is really massive in size. It's about 3 times the size of Texas and close to 2 miles thick, its ice in its deepest part. It's the second largest continental ice sheet on Earth after Antarctica. Contains so much ice that if it all melted, sea level would rise by about 24 feet, which is particularly concerning since we now know that the Arctic is warming 4 times faster than the rest of the planet. It's really hard to get your mind around that size. And even though I've traveled to Greenland dozens of times, it still seems vast and remote to me.
All right, there's a lot to unpack there. We'll get into more of that a bit later on. But first, Isabella, tell us where you work.
So I study the Beaufort Gyre, which is this vast clockwise circulation feature in the Canada Basin. And this feature really sets the temperature, salinity, and sea ice through a lot of the Arctic. And it's also the freshest part of the Arctic. So you can think of it as this big rotating bowl of relatively fresh water compared to the rest of the ocean. And it's important because it impacts the way that the ocean interacts with the atmosphere. In this region, it can affect currents downstream when fresh water is released from it. And through these interactions with the atmosphere and the rest of the ocean, it can impact the global climate in addition to local weather.
Okay, and Evie.
Yeah, so I work in the Bering Sea and the Chukchi Sea, and also in the Bering Strait, which is this narrow passage that connects those 2 bodies of water and runs between Alaska and Russia. And I work on a toxic species of phytoplankton. When I say phytoplankton, I mean these little single-celled algae, kind of like plants that float around in the ocean. Most of them produce oxygen. They're really good for the planet, but some of them can cause harm when they grow into really big, dense blooms. The one that I work on is called Alexandrium catenella, and this is a species that creates a potent neurotoxin that can actually build up in the organisms that eat the algae and cause illness in people or animals that eat that contaminated seafood. So we call that paralytic shellfish poisoning, and in recent years, we've seen that these big blooms of Alexandrium are actually happening in Arctic waters.
All right, we'll get into more of that soon too. But before we get into more detail about your work and the implications of all of your findings, I want to give the audience a little bit of a sense what it's like to work in the Arctic as a scientist. I know we have some images to share, but Isabella, how do you study a massive icy current like the Beaufort Gyre?
Yeah, so the project I work on is a collaboration with some Canadian colleagues, and we actually work on a Canadian Coast Guard icebreaker. So you need this really massive, unique ship that can break through the sea ice in order to get to the places where we want to take our measurements. The ports that we go out of are not big enough for this ship to dock on, so we will board using helicopters or barges. Board
the ship using a helicopter.
We board the ship using a helicopter.
Okay.
So this is actually one of the Canadian Coast Guard helicopters that I used 2 years ago to get on board the ship. So that image is from the helicopter as we're approaching the ship. as a big group of people on the ship. We live on board for about a month or so, and we're taking all sorts of measurements, but the ones I'm focused on are really temperature, salinity, and velocity of the ocean to understand the physical movement. So we get these yearly maps with that CTD rosette you can see in the picture. We can make these big maps of what the Beaufort Gyre looks like each year.
What does CTD stand for?
Sorry,
Oh, sorry.
CTD. It stands for conductivity, which is how we measure salinity, temperature, and depth. So just the three main things it measures. And then we also collect water, and you can get all sorts of other measurements out of the water. Yeah, so we build these maps with that rosette, and then we also leave these moorings. So what you're seeing here is the top float of a mooring. We leave those underwater for a year at a time, and that way we get a sense of how things are changing underneath. And finally, we also actually deploy instruments in the sea ice itself, and they take measurements underneath the sea ice, and those drift along with the sea ice. Those are called ice tethered profilers. So those are kind of the three main platforms that I use.
Pretty cool engineering. Had to go into that. So Evie, similar question to you. You work in the Arctic studying HABs. How do you do that? Are you on a research ship like Isabella? How do you even study microscopic little plants or know whether an algal bloom is harmful or not?
Yeah, so we do most of our work on research vessels similar to Isabella. We go up mostly in the summer and fall, so we don't necessarily see a lot of ice, but we do run into it sometimes. So we go on icebreakers or at least ice-capable vessels. And when we're out there, we collect water samples and also mud samples to look for the toxic algae that we study. We'll bring those back to the lab, and we'll use microscopes to check them out and see who's living in there, and also analyze them for those algal toxins that I'd mentioned before. And we work really closely with physical oceanographers at WHOI to not only understand where the algae are, but also use wind and current data to understand where these blooms are coming from and where they might be going. So a lot of our work does involve taking these samples on the ship and bringing them back to Woods Hole, but we also have an instrument called an imaging flow cytobot, or IFCB. It was actually invented by Heidi Sosik here at WHOI, and it's this really cool robotic microscope that actually takes in water samples and images all of the different algae and phytoplankton in that sample in real time, and it works 24 hours a day. It collects thousands of images per hour, and when we're out on these research vessels, we can configure it to sample from underway seawater so that we can actually see what's in the water as we're moving along, and that allows us to potentially identify some of these harmful algal blooms in real time, which is something that wasn't possible 10 or 15 years ago.
Neat. Sarah, how about studying ice sheets and glaciers? Where do you live when you're doing research in Greenland on the ice, and how do you track changes looking at ice?
Yeah, that's a great question. So, Greenland, as I mentioned, is a really enormous and vast place, and the island is almost entirely covered by ice. But there are small towns that surround the ice sheet. This is where the people of Greenland live, and where we're fortunate to be able to travel through and work out of. So we'll fly into Greenland. Actually, anyone can buy a plane ticket to Greenland. It's not like the Antarctic where it's restricted. And it's quite a tourist destination. So some of you listening may want to check it out someday. But from these small settlements, like the town of Ilulissat shown here, we'll take airplanes or helicopters up onto the glaciers and ice sheet themselves, or we may take a small boat up the fjords. And using these aircraft, we get put out on the ice. And for some projects, we will do our work during the day and return to the towns in the evening, where we can have a warm bed and a hot meal. But for many of my projects, we may be out on the ice for weeks, up to a month at a time, to carry out our work. So the plane or the helicopter flies away, we set up tent camps, and we are there. Very self-sufficient. If something breaks, we have to fix it. We have to do our own cooking, and we sleep right on the ice. So we're really doing it all at the same time. And the kind of work that we're doing, we use a variety of tools. It really depends on the kind of science questions that we're asking. So some of the work that I do, such as shown as this picture, is ice coring. I like to refer to ice cores as a time machine. They allow us to go back in time as travelers through time to investigate how past changes in climate have impacted the Greenland ice sheet, how much snowfall there was, how much melting there was, how the chemistry of the ice has changed in response to other changes in the environment. And this tells us a lot of clues about how Greenland responds to climate generally, and that will help inform us as to how we expect Greenland to change in the future. Some of the other projects I do are much more focused on the present, and so we're trying to use, for example, precise geophysical tools like GPS or seismometers to understand how the ice is flowing through time. And here time, we're talking about seconds or days or months or years versus the thousands of years we might look at in an ice core. And we can see how small amounts of melting from warmer summers cause the ice sheet to speed up and move much more quickly into the ocean. And we can also use some of these tools to try to peer underneath the ice. So under a kilometer or more thick ice, we want to understand how the water that forms on the surface is moving around underneath. So we have to use sensitive equipments like seismometers shown in this image drilled into the ice to try to detect this water flow remotely through the ice sheet. And then finally, we're interested in—
before you go on, I'm curious about seismometers being used on ice. So I think of seismometers as looking for, feeling the vibrations of earthquakes, right?
Yeah, so it turns out that when ice cracks or water moves through the ice down to the bedrock below, it also sends out energy. And it's not quite the same energy that an earthquake would, although you can pick up earthquakes as well using seismometers in Greenland. But we're looking for much smaller signals called seismic tremor, which we're actually in the midst of a project right now where we're trying to use that seismic tremor to map out how the water moves underneath the ice out towards the sea. And then when we get to the coast itself, we use small ships to try to get right up, or sometimes autonomous vehicles to get right up to the front of the glacier and monitor the meltwater that's coming out under the water, how that's affecting the dynamics between the ice and the ocean, as well as what that means for the fjord and the ocean system itself. So in this photo, you see a tool called the Jet Yak, which is an autonomous system built just on the back of, if any of you ever go on a sit on top kayak, but it's kitted out with all sorts of sensitive equipment. And the Jet Yak is a platform that allows us to go right up and bump right up against the front of the glacier without a person on it. It's a very dangerous environment. So allows us to take measurements at that interface where we really wouldn't have had any other way to do it. We wouldn't want to take a ship to the front of a calving glacier. So a wide variety of tools help us peer into, under, and around the ice.
Fascinating stuff. I want to ask our behind the scenes Q&A manager, Ken, do we have any questions from the audience yet? Or should we keep going?
Oh, no, we have quite a few questions coming in already. There was one specifically for EVIE from AC, who asks, can you distinguish among different types of blooms with satellites, especially between phytoplankton blooms or those that produce toxic compounds?
That is something that people are working really hard on right now. And so there are different wavelengths of light that these different phytoplankton species reflect, and you can pick up some of that when you look at satellite images. The group of algae that we study is called dinoflagellates, and they tend to reflect very red light. So when you see them from space, they kind of look brown or red. And so you might know from that there's a dinoflagellate bloom happening. It's really, really hard to pick out specifically exactly which species is causing that. So I think satellite is a tool that can be used in combination with other things like water sampling or the imaging flow cytobot. You could have someone say, hey, I see a big bloom in this region, someone should go check that out. And then it needs some ground truthing, literally ground truthing, to understand what that actually is. But it's a really cool and exciting field.
Then can I ask another one?
Ahead. Yeah,
okay,
I was
so
just
this
going to
is
say that was a great question.
This is going to lead into the next part of the discussion, I think. Marcus asks, why is the Arctic warming faster than most other parts of the planet?
That was something you said, Sarah. So do you want to take that?
Yeah, so there's a number of factors, but one of the key ones is that is something called the albedo effect. So as the Arctic warms, you start to transform a landscape that's been very white and bright and can reflect a lot of sunlight back to space to one with a darker surface. So whether that's losing snow cover over land or losing sea ice over the ocean, and that warmer areas or that lower albedo, less reflective areas absorb much more of the sunlight. So that's one of the factors which is leading to what we call this Arctic amplification.
All right. Yeah, I do want to get more into some of those changes that you've been observing in your work in the Arctic and the implications for the rest of the planet. EVIE, so harmful algal blooms get quite a bit of news coverage, but I usually think of them as affecting warm water. So we get some harmful algal blooms here on Cape Cod in the summer, and you hear about them, big ones off of Florida, but is it really a big problem in a cold place like the Arctic?
Yeah, that's a great question. So the species that we study in Alaska is actually the same one that causes shellfish toxicity every year off the coast of New England in the Gulf of Maine. That species blooms all over the world, but generally at more temperate, like mid-temperature latitudes, and very occasionally in polar waters, like in Norway, they have some blooms and toxicity. So we know that there's actually a very long history of these blooms further south in the Gulf of Alaska, and only in really recent years have we started to see these big blooms happening in Pacific Arctic waters. There's a few possible reasons for that. One is that we're seeing increased flux of water through the Bering Strait. That's that narrow passage that I talked about before. And as you have more water passing through, it's bringing more heat up north, and also more of these temperate species are having the chance to hitch a ride into polar waters. So this diagram is actually a really great illustration of that. We think that blooms are actually starting further south and then getting swept up north into the Chukchi Sea. We also know that bottom temperatures in the region are becoming warmer and warmer very rapidly. And this species actually has a benthic or a mud stage. It starts from the mud. It has this little dormant form called a cyst. It's kind of like a seed that sits down in the sediment. And when water temperatures become warm enough, that signals those seeds to release cells and start these toxic blooms. If water doesn't get warm enough, they'll just sit there dormant in the sediment for 1 year or 10 years, or even up to 100 years. They can stay alive and inactive, waiting for the right conditions to form a bloom. So as we're starting to see these warmer temperatures in Arctic waters, it's becoming more and more likely that we could actually not only have blooms being swept up from the south, but also have blooms starting in those northern waters as well.
And when you've been up there, how have you been seeing these blooms affect people and wildlife in the Arctic?
So there's been a lot of research showing that these toxins are present throughout the food web, all the way from fish and krill to marine birds and mammals. In 2022, so just last summer, we were up there for kind of like a routine harmful algal bloom cruise. And as we were getting underway, the imaging flow cytobot started to detect really high concentrations of Alexandria, much denser and more widespread than anything that had been detected in the region before. So we immediately got in touch with our collaborators in Nome. We let them know that there was a harmful algal bloom happening in their waters. And we were able to work with them to release a risk advisory that could actually be distributed to coastal communities and allow health organizations to get up and running and prepared for any possible illness. Luckily, that didn't happen. People got that advisory and they were able to avoid eating things that could potentially be toxic. And as far as we know, no one became sick. But it's really disruptive when you find out that there is a bloom like this happening in your region. In other parts of the world, the main vector for these toxins to reach people is through shellfish. That's why we call it paralytic shellfish poisoning. But in Alaska, people aren't just eating shellfish, they're eating many different marine organisms, fish, marine birds, walrus, bowhead whales. And so there are all these other potential vectors that could be accumulating and potentially exposing people to toxins. And we really don't know very much right now about how these different organisms are transferring these toxins. It's something that we're working hard to build a knowledge base for. And I also want to mention that in this region, subsistence is a way of life. It's the way that people are feeding their families and providing for their communities. So having a bloom like this occur is extremely disruptive. It can cause people to forgo things that they would normally eat and maybe go and spend more money at the grocery store. Groceries in remote communities in Alaska are extremely, extremely expensive. So it really adds a cost to and a burden to those communities to be facing something like this. So yeah, it's something we're working to build a knowledge base for, and hopefully we can find out more about when and why these blooms are occurring so that people can appropriately manage the risk and decide where and when and what is safe to eat.
Thanks, Evie. So you've been talking about one of the impacts of a changing climate on people who live in the Alaskan Arctic. As we saw in the pre-show, almost 4 million people live in the entire Arctic region. Of those, roughly 10% are indigenous people who encompass more than 40 different ethnic groups. Folks in the audience might be familiar with some of their names: the Inuit of Greenland and northern Canada, the Sami of northern Scandinavia, or the Yupik of Alaska and eastern Siberia, but there are many more. We want to share a video message with you now from one Arctic resident. Her name is Piama Olair. She lives in the Aleutian Islands off Alaska. We asked Piama to share her observations about the impacts of climate change in her part of the world and how it's impacting her community. Here's what she said. I don't know if we're having trouble getting that video to run. We can come up. Here we go.
Hi, my name is Piama Robinson Olair. I'm from Unalaska. I had the opportunity to travel the length of the Aleutian chain from actually from Unalaska to Adak and back on the Sukuliak, the research vessel. And every port, or not, they weren't ports, every cove or harbor that we disembarked in, I got a chance to go to land. I was shocked at what I saw. All along the way, we should have hundreds, if not thousands, of waterfalls, and I might have counted maybe a dozen in the entire 800 miles that we traveled. And every place that we stopped and I had the opportunity to hike the hills, I found extreme drought conditions, and that's never been seen in our people before. I asked one of our elders if he had ever seen drought, and he asked all his elders, and he had never seen any. It's not in our language, extreme drought. It's just not something that we've had to contend with. He said that he had fished or hunted at the same lake every year of his life, and when he showed up to the lake, there were no ducks because there was no lake. That's never happened before, and nobody ever remembers it happening. Anyway, those are our climate concerns in the Aleutians.
Anybody want to comment on Piama's observations? You might be wondering why Piama was standing in the rain and snow talking about drought, but she actually made that video for us in Anchorage, Alaska, which is about 800 miles from her home in the Aleutian Islands. And she mentioned how nice it was for her to feel that rain falling. They've been having really unusual conditions in the Aleutian Islands. I mean, drought just isn't, it's a very wet area normally, and to see drought there is pretty unusual.
Yeah, it's really hard for me to imagine, having traveled to Alaska a couple of times, imagine that area in drought. And I think really speaks to the dramatic and unprecedented changes that are being seen all across the Arctic. can be very unsettling.
So changes in the Arctic obviously have profound impacts on the people who live there. What might be less obvious is how a changing Arctic affects the rest of the planet. Sarah, I want to stay with you. In 2018, you co-authored a paper in the journal Nature about the melting of the Greenland ice sheet. I'm going to read the first sentence from an article by John Schwartz in the New York Times about that research. Schwartz wrote, "Greenland's enormous ice sheet is melting at such an accelerated rate that it may have reached a tipping point and could become a major factor in sea level rise around the world within 2 decades." I know that at the time, Sarah, you didn't agree with the use of the phrase tipping point. We'll come back to that in just a minute. But how fast was Greenland's ice sheet melting then in 2018? And what's happened in the 5 years since then? And what are the implications for sea level rise?
Sure. Yeah, that was a really important study in the sense that it used a combination of satellite records, computer models, and notably ice cores to allow us to put the recent melting observations of Greenland into some longer context. So we've only been able to observe changes in the mass of the ice in Greenland precisely using satellites for the last couple of decades. And what that has shown us is that Greenland has gone from a period of relative stability where the ice was what we call in balance. It was growing and shrinking about the same pace. So prior to the 2000s. But starting in the 1980s or so, Greenland started losing much more ice than it gained every year, leading to this imbalance. And that's what's making Greenland now one of the largest contributors to sea level. And as you see in this graphic, as the colors expand, this is an animation made by NASA showing how much the ice is thinning around Greenland. This is from about 2002 to 2023. And the brighter and darker colors indicate the areas where the ice is thinning most rapidly. And as you can see, as we march through the last couple of decades, the ice has continued since our study period and over this observation area to continue to be lost. What we were able to show in addition is that this is a really recent phenomenon. And so we could go back with our set of observations and demonstrate that the increase in ice loss and this increasing contribution to sea level rise really only started to ramp up after the post-industrial era. So when humans and our sort of energy economy turned towards emitting fossil fuels into the atmosphere. So we were able to demonstrate that since the mid-1850s, the amount of ice discharge, so ice and meltwater, had increased by 50% and by 30% just over the 20th century. So put it into this longer context. And really what that means for the world now is, as Greenland is a growing and now leading contributor to sea level rise, and we expect that to only accelerate into the future as the Arctic and Greenland continues to warm. Greenland loses a tremendous amount of ice per year now, more than it gains. The average over the last 20 years, where we have very precise measurements, is about 270 billion tons per year, which again is a number that's impossible to get your mind around. I saw a nice way of illustrating that today that I'll offer up to you, which is it's about the size of 3.5 Olympic swimming pools of water every second of every year is how much water Greenland is adding to the ocean. So it's really an incredible number and increasing contributor. And as climate warms, it's going to be growing even further.
All right, Isabella, let's go to you now. Help us understand what's happening in the Beaufort Gyre, or maybe I should say what isn't happening that is supposed to be happening.
Yeah, so as I introduced a little bit earlier, the Beaufort Gyre is this sort of bowl of fresh water that's spinning around clockwise. And it accumulates fresh water that pours into the Arctic from all of the rivers that drain into the Arctic. Sea ice melt, rain, and Sorry.
No, that's okay. So that's where the fresh water is. That's
That's
why
where the
it's
fresh water is
fresher.
coming from. So it's fresh water is coming into the Arctic. It's accumulating in the Beaufort Gyre, and this bowl is thought to sort of speed up and slow down, speed up and slow down, and that kind of regulates the when it speeds up, it accumulates fresh water, and when it slows down, it releases fresh water. So that is thought to be on this 5 to 7 year cycle. And my colleagues here at WHOI started measuring the Beaufort Gyre in details about 20 years ago. And they were expecting to see this cycle that sort of was known about historically. So they went up there, they saw this accumulation that sort of reached its peak in about 2008, 2010. And ever since then, we've been waiting for the release. So, is it going to be this year? Is it going to be the next year? So instead of this 5 to 7 year cycle, we now have had over 20 years with no release. Still waiting for that to happen and trying to understand, why it isn't happening.
And so how likely is it that we're going to see a release soon? And what will happen? So I assume there's been more and more fresh water accumulating. So it's kind of a different scenario than the cyclical pattern that was happening before. What would happen if the Beaufort Gyre suddenly released all of that fresh water?
Yeah, so it has sort of plateaued. It's not like endlessly accumulating right now, but it could have pretty big consequences if it were to be released. So just to be clear, this graphic here is showing sea ice movement. So you can see that clockwise rotation sort of north of Alaska. That's the Beaufort Gyre moving that sea ice clockwise. And then a lot of that sea ice then flows out east of Greenland. So that's actually a way for getting fresh water out of the Arctic that is ongoing. So the Beaufort Gyre releasing more fresh water would be releasing fresh ocean water underneath that, sort of with a similar pattern to what you see in the sea ice. And the reason we think that could have big consequences downstream is that fresher ocean water is a lot lighter than the rest of the ocean. So the Atlantic is a lot saltier than the Arctic. And if you add fresh water to the Atlantic, then that could disrupt the stability of the water column there and make it so that less deep water is formed in the Atlantic. So in the Atlantic, water gets really cold and sinks to the bottom of the ocean and then takes part in this large scale ocean circulation called the Atlantic Meridional Overturning Circulation, or AMOC for short.
It's been in the news lately.
It's been in the news lately.
Yeah.
So this AMOC circulation helps to regulate the Earth's climate. So it could be that a Beaufort Gyre release of fresh water would slow down the AMOC and affect the climate, particularly in Europe, which sort of benefits from the AMOC. It keeps Europe warmer than it otherwise would be. So we really, we're trying to understand how the Beaufort Gyre works and how ocean circulation works in general. So we don't really know what to expect, but we're working on understanding it better so that we can better make these predictions.
All right. Ken, do we have any more audience questions?
We do. Let's see. Cameron, in Dr. Coleman's Intro to Oceanography class at UMass Boston, wants to know, what do the panelists think is currently the biggest obstacle when it comes to addressing the changes that they're seeing in the Arctic? Is it resources, policy decisions, public awareness, or is there something else that might be a bottleneck to change?
So addressing climate change in the Arctic.
Can I say yes to all of the above?
Sure.
Yeah, I think, all those things that, the Arctic is a really tricky place to work. So the resources that are needed to access the areas where Evie and Izzy and I all work are tremendous. And so there, there aren't really enough observations yet to fully understand the system. So we need to do more there. The Arctic also feels very remote to most people, and perhaps different and not connected to the rest of the world, and maybe not as important. So I think there it's also important to understand that the Earth and the oceans all operate as a system, and everything is connected through the atmosphere and the ocean. And so the Arctic does matter to all of us.
And I'll add too that it's really important for us to understand the details of how all these systems are working, and make predictions. But there are many things we know for certain, and we're not waiting on the science for, such as the melting of Greenland that Sarah was talking about, and the melting of Arctic sea ice, and the warming of the Arctic. Those are unequivocally observed, and it's important to state that too, even though we're working to understand the
signals are large.
Can I ask another?
Yep, go ahead.
Two people, Diana and Emma, asked roughly the same question. They're wondering, sort of leveraging off of Piama's comments, how do you as scientists engage with local communities, and how do you incorporate indigenous populations or indigenous knowledge into your data and your observations?
It's a great question. Evie, we heard a little bit about how you had the opportunity to work with local people in Alaska. Does anybody else want to take the question?
Yeah, I haven't had the chance to interact very much with the local communities, where we're usually up on the ice sheet itself, where nobody lives, and while it may look close on a map, it's pretty inaccessible to anyone from the areas where we're working. But certainly, just by spending time repeatedly in the same kinds of small towns, you start to listen and hear from local communities about what changes are impacting them, and similar to what some of the other panelists have mentioned, the changes in the sea ice conditions, the iceberg calving, and all the changes in the ocean. The people of Greenland are very dependent on the sea, both for transportation and for fishing, both as their economy and their livelihood, and feeding their own family. And they've been greatly impacted by just in the last couple of decades by diminished sea ice. And in fact, when you have more calving from the large icebergs, you also have, from the large glaciers, you have many more icebergs in the bay themselves, and those can pose a hazard to the small boats that they take around. And then they also have many fewer days that they can use their dog sled teams to go out on the ice. It's just not safe. So they have conditions where there's enough frozen sea ice that you can't use your small fishing boat, but it's not stable enough to use a snowmobile or a dog sled. And so they're really isolated from a resource that they're quite dependent on.
I can
Yeah, go ahead, Isabella.
Just that with our program, we also could interact more with the local communities. It's, again, we're pretty far offshore, so not import much, but we do make presentations to the Alaska Eskimo Whaling Commission yearly, and so we communicate with them about science, and we also hear what they're seeing changing in the ocean locally, and we also communicate with them about their yearly whale hunts. So we communicate to shore and sort of ask, we're going to be coming within 50 kilometers. Like, is this an okay time for us to be here? Or do you have boats we should be looking out for? Things like that. But we would definitely like to make closer links with the local communities.
Evie, how can coastal communities in the Arctic become more resilient to, in your case, harmful algal blooms?
So for the harmful algal blooms very specifically, I think there's a really big need for better infrastructure for testing of seafoods and water samples to find out when those toxins are happening. Right now, if someone in Alaska harvests something and they want to know whether it's toxic, if they're in the Bering Strait region, they have to ship their sample all the way down to southern Alaska. That can take weeks, and in the meantime you're left with this huge question about whether or not your seafood is toxic. So actually having resources that are centralized in the communities and the ability to do that testing themselves would be really huge, and it's something I know our partners are working really hard on getting running. Also just building up offshore monitoring with imaging flow cytobots and other instrumentations so that there can be early warning of these blooms when they're happening. Once again, learning more about how these toxins are passed through the food web would go a long way towards helping people manage risks. And in other parts of the world, they can actually use environmental and biologic data together to actually model and forecast blooms, like kind of the way you would with a weather report. Exactly. So I think we're starting to get to the point in the regions that we work in Alaska, where we have enough mud data and water data and all these other oceanographic parameters that could potentially be put together into some sort of forecasting. It takes a long time to get those models into something that's really usable for stakeholders. That's kind of a longer view for the region. But those are a few potential solutions. A lot of the time people ask if you can stop these blooms, and unfortunately, once they get going, it's not like we can just, I don't know, scoop them out of the water or like sprinkle something in the water to make it disappear. It's really more about just managing risk and making sure that people are being safe.
Makes sense. Sarah, I want to go back to the concept of tipping points that we raised earlier. Why didn't you agree with calling the rapid melting of the Greenland ice sheet in 2018 a tipping point? And haven't we passed the point of no return when it comes to melting ice and sea level rise?
Yeah, that's an excellent question. So I think the best way to answer that is the reports that came out, such as our paper in 2018 and many recent papers since then, what they've really identified is that the melting Greenland is dramatically increasing. It's accelerating faster and faster, not necessarily every year, but sort of in an average sense. But that is different from a tipping point. So what that means is that as the climate continues to warm, Greenland's going to melt faster and faster. And so we are going to lose ice in increasing capacity. But what a tipping point suggests is that we've entered a new state where the ice sheet is actually responding in a different way to warming. So for example, if we were able to stabilize climate by stopping emissions, that Greenland would just continue to be lost forever. And we haven't reached that state yet, which isn't to say there isn't a path there, but actually gives me a lot of hope that we haven't passed the tipping point for Greenland or for the Antarctic. But it's one of the reasons that as scientists, we really argue strongly for keeping the planet on these pathways. Some people may be familiar with the targets, say from the big UN climate conference in Paris, the Paris Agreement, to try to stabilize global temperatures between 1.5 and 2 degrees Celsius warming. And the reason that we're so insistent on that is that there are a lot of tipping points that happen, whether it's in the ice or in the Amazon or permafrost after that point. So we have ways to reach those goals. We know actually that if we can stop CO2 emissions entirely, which I realize is a large ask, global temperatures will stabilize, very quickly. Some models suggest within years. So there's a lot of hope in that as well. Where there is some caution is that right now.
Well, I've at least lost you, Sarah. I'm not hearing you. You might want to turn off your video. All right, we've lost Sarah for a second there, but so we'll come back to her. But Isabella, is there anything you'd like to say about this topic?
Looks like she's back, so I'll let her finish her thought.
Okay, sorry, Sarah. Go ahead.
Sorry.
No worries. I I was going to say that this all, hearing you talk about this, it sounds more than just sort of like an intellectual or academic exercise for you. It sounds pretty personal.
Yeah, I think it's important as a scientist to recognize that we're studying this topic not just from the lab or from the field, but as part of the many communities with which we inhabit. And so, for me, I feel like I'm a scientist, but I'm a mom, I'm a member of a community, I'm an educator. And so I feel that climate change is the crisis of our generation and is really something that I want to tackle from all those different levels. And so that's led me to act in a lot of different ways to try to help change the path.
Well, we've lost you again. You might want to keep your video off. I was going to say, I know Sarah took students last year to the UN climate change conference in Sharm el-Sheikh. COP27, and I know she's going to go again this year to COP28 and bring some more students. So that'll be great.
Yeah,
there you
my
are.
bad. Sorry about that. Getting close to the end of the hour. Yeah, so I've been involved in taking our students, our fantastic students, to the UN Climate Conference. And that's one of the many ways at which we can sort of build up the next generation of leaders in ocean and climate science.
And I know you belong to an organization called Science Moms. What's that?
Yeah, so I want to point anyone who's interested in solutions for themselves or their families towards the website for Science Moms. It's a great national nonpartisan group of many of us who are climate scientists and moms who really just want to share tools and unbiased information for everyone to learn and figure out how they can help contribute to creating a safer planet for not just our kids, but for everyone in the future.
All right. Now, Isabella, do you want to add anything to this discussion?
Yeah, I just wanted to highlight, that these measurements that we're taking in the Arctic, they are really important long time series that we need to keep up. The Arctic is one of the least sampled oceans, in part because of the sea ice, really. It makes it very difficult. It's very hard to get to, very harsh conditions. And so these long time series are really critical to keep them going and continue to monitor our climate. Because they don't just happen on their own. They really require a lot of investment and hard work.
All right, Ken, let's take a few more audience questions.
Okay. Ms. Towns' class at Edward Little High School in Auburn, Maine, sent a couple in. The first one is a student is asking that they saw something on TikTok about Arctic sea ice melting completely over the next few years and wonders, is that true?
Well, first of all, I think when you see things on TikTok, it's a great question to ask, is that true? And then Google and try to look for some more reliable sources. But it's partly true. The science suggests that within the next couple decades, we will have a sea ice free Arctic in the summertime. So that doesn't mean that there's going to be no sea ice in the Arctic ever. It's just that historically, sea ice has lasted from year to year. And in the future, it seems that sea ice will just be formed in the winter and melt completely in the summer. We will probably see that in most of our lifetimes.
And that'll have a big effect on the albedo effect that Sarah was talking about earlier.
Yeah, it'll be a whole new regime.
Yeah. Anything else? Oh, actually, let's. So Erin Towns, you know her, right, Sarah?
I do. So Erin is an absolutely fantastic, wonderful human being who I was really fortunate to work with in Greenland through a program where we can take teachers up into the Arctic with us through a program that was called Polar Trek and is now transitioning to Polar STEAM. And so I had the great privilege of working with Erin and also interacting with some students from her school. And she traveled to Greenland with us last spring in 2022 and spent almost a month working up on the ice with us. She was a full member of our team. And if you go to the Polar Trek website and look up Erin Towns or Greenland, you'll see her posts where she tried to share this experience.
All right, we've lost Sarah again, but Ken, I think we have one more question from that same class.
Yeah, since we have an all-female panel, one of the students happens to ask, what's it like for a woman scientist working in the Arctic? What was difficult or challenging about it?
I can start with that. So I'm kind of on the younger end of the science spectrum at this time in my career. So I've actually been really lucky to have lots of great experiences at sea with lots of other women scientists and women on the crew of the ships that I've worked on. And I've been lucky to always feel like really comfortable and safe at sea, but I know that that hasn't always been the case, and not just in the Arctic, but in lots of oceanographic research, women weren't always welcomed. And I think there is still a lot of work that we can all do to make sure that field environments are safe and welcoming places. But I think the difficulties I've had in my field experiences have been less because I'm a woman and more just because working in the Arctic is hard. And there are a lot of challenges that come with working in extreme polar environments.
Any other questions, Ken? I think we have time for one more.
Oh gosh, yeah. We're approaching 100 questions.
Wow.
Let's see. One person noted the jet yak. This is from Catherine. Building off the jet yak, which is sent out to glaciers mentioned by Sarah. What other new technologies, sensing equipment, or innovative tools are being used in Arctic research and in your areas of research?
Anybody want to take that?
And you might want to mention the backstory of jet yak, Sarah, because that's kind of interesting.
The backstory of jet yak. Yeah, so that was not developed to be used originally in a place like Greenland. I think that just shows you how you can use tools that were designed for one particular set of questions, and then used in different environments. And it also stems from the fact that putting really sensitive equipment and robots in ice environments is quite dangerous. And if you put a very expensive platform in, it can get lost easily, and you may lose hundreds of thousands or millions of dollars in an instant. And so the premise also behind the jet yak was to use something that you could, literally go and buy down the street at your marine store and put relatively low cost instruments on, and thereby allow us to test it out in really high risk and novel environments for the first time. The other thing we've really found in our work, the field I'm in, glaciology, is small and relatively new compared to a lot of, for example, the geology and geophysics community. And so it's also been really nice to take tools that have
Nope. I think we lost Sarah again. I actually wanted to mention those ice-tethered profilers, Isabella. That they're not new, but I think they were pretty innovative when they were first developed, to be able to put something out on the ice and working in those conditions and have it stay out there for long periods of time and not break down is a pretty impressive feat.
Yeah, those were developed at WHOI as well. I think and in large part by my PhD advisor, John Toole. Part of the difficulty of working in the Arctic, like I said before, is the sea ice. And you worry about sea ice can ridge and mess up your instruments that are down below. So you don't want to have instruments hanging out too close under the sea ice. So I think the thought was, well, why don't we use the sea ice? Instead of sort of working against it, let's work with it, and let it take our instruments around, and show us what's going on underneath the sea ice.
Yeah, very cool. Sarah, we lost you partway through. Did you get to say everything you wanted to say?
I think I was just trying to come back around to the fact that we can also use existing tools that are in more established fields, like seismometers used for earthquakes, and apply them in new ways to new environments, like on the ice. So there's a lot we can learn from that, as well as developing new sensors.
We're running out of time, but I do want to ask, is there any tool that you wish you had that hasn't been developed yet?
Oh my goodness. Well, a real-time machine would be incredible, I think, to go both forwards and backwards. See what the future has in store for us.
Okay. We're almost out of time, but I do want to end with one question for all of you. What would you say to a young person in our audience who might be thinking, how can I join your team? Or how can I get to go to the Arctic and do some research there? Keep your answers short, but Isabella, why don't you lead off this time?
Sure. So my path was pretty nerdy, maybe. I started off in math and physics. I really enjoyed science, sort of basic science. And then once I got my bachelor's, I was like, well, now what do I do? So I really wanted to do something that connected more with the natural world, and especially because of climate change. So that's actually turned out to be really useful to have a sort of a basic science background. So I'd encourage you to learn science well, and then you can apply that to so many different things.
Evie, you're getting your PhD right now. What's that like? And is getting a PhD the only way to do research in the Arctic?
I'm having a great time so far in my PhD. It's been great. But I actually didn't start as that. After finishing my bachelor's, I was a research assistant working with my advisor, Don Anderson, and that's actually how I went to the Arctic for the first time. I got sent up in 2018 to start sampling the Chukchi Sea, and found that there was so much interesting stuff going on up there that I wanted to stick around and keep on working on that for grad school. However, there are plenty of people who have really successful careers as technicians or as ship's crew, and I've been lucky to work with a lot of these folks in my various capacities on these cruises. That's a great photo there of all the people on the Norseman crew last summer, and I think I was maybe the only student on that boat. So everyone else you see there found other ways to get up to the Arctic. We had one technician in our lab who went up 5 different times this year. So yeah, you can get there even if you don't want to go to grad school.
Sarah, you talked about polar trek or polar steam earlier. Anything else you'd like to say to younger folks who might be watching right now?
Yeah, I guess the other thing is, even if you're not interested in becoming a scientist or even necessarily traveling to the Arctic, there's a role for all of us to play in protecting the Arctic for the future. And so whatever field you're in, whether you're a writer or a lawyer, or doing anything, every company now is starting to look towards sustainability. Every decision you make in your personal life will have an impact that matters. Every conversation you have with a neighbor, friend, family member will help us create a future in which the Arctic is protected and there for everyone.
All right, we're going to have to leave it there, unfortunately. I want to say a big thank you to Sarah Doss, Isabella Labras, and EVIE FACHON for joining us tonight to talk about their work in the Arctic. Thank you also to my WHOI colleagues, Ken and others who have been working very hard behind the scenes to make this event possible. And to everyone who joined us on Zoom, Facebook, and YouTube, thank you. Tonight's event was the 5th in our 5th season of Ocean Encounters. Our next Ocean Encounters, the season finale, is scheduled for October 18th, and it will be about careers in marine biology, so I hope a lot of people will join us for that. We actually have something special planned for that event. We'll be doing it online, as we normally do, but we'll also have an in-person audience in Woods Hole. So if you're in our area, please come and join us there. And you can watch our website, whoi.edu, for more details about that. In the meantime, you might also want to take a look at the very cool merchandise at WHOI's online store. That's shop.hui.edu. You get a 15% event discount for joining us tonight. Just type in the discount code Arctic. We do know that there are no penguins in the Arctic, but that special edition penguin t-shirt was created in honor of Climate Week, which is happening right now. And during Climate Week, if you're not yet a WHOI member and would like to become one, your membership gift will actually be tripled up to $50,000 thanks to the generosity of a dedicated WHOI life trustee and his wife. Memberships start at just $40 a year. The average gift is $120, but any amount helps. You'll be providing crucial support for our outreach and our science, and you'll get some great benefits in return. If you are already a WHOI member, thank you again. Your support makes a big difference. That's our event for this evening. On behalf of Woods Hole Oceanographic Institution, thank you and good night.
Out where the seas are the deepest and the mysteries the greatest lies our future. The ocean is our last unexplored, ungoverned frontier. The life support system for our planet, inextricably linked to our climate and weather, and to the lives and livelihoods of countless people around the globe. But even against the ocean's vastness, humankind can be a formidable force. What happens next demands action that is rooted in scientific understanding and unvarnished truth, because our world stands at a fork in the road. In one direction, we watch the ocean being catastrophically altered beyond its ability to sustain us. In the other, understanding outraces exploitation, and we help steward and protect this most precious shared resource. What will be the legacy of the 21st century? Together, we can unleash the world's most creative minds, passionately dedicated to ocean science, engineering, education, and policy. Together, we can provide the expertise needed to know what works and a trusted voice to present the facts as we uncover them. Together, we can shape the future. We can inform governments, businesses, and conservationists. We can generate new knowledge in service of society. We can be the catalyst for change. It is more than our responsibility. It is the defining moment of our generation. We are explorers, students, and stewards of the ocean, and this is our time.